Hello students, in this video we'll use the Cauchy Integral Formula to prove that holomorphic functions are regular functions. Let me explain what that means. Let me just say it in words first. For a function, if I say regularity theory, that means suppose I say a function is differentiable, i.e. f prime exists. That doesn't give you any indication if f double prime exists or f triple prime exists, but the remarkable fact about holomorphic functions is that holomorphic means that f prime exists, period. What Cauchy's formula gives you is that if f prime exists for a holomorphic function, so does f double prime, so does f triple prime, so does f quadruple prime. All the derivatives exist, and even more is true than that. So it's called a regularization result. So this is our regularization theorem. Regularization theorems are extremely valuable, right? So if you were able to prove that solutions to the supercritical surface quasi-geostrophic equation were eventually regular, you would probably get a PhD thesis, right? Sorry. All right, so what's our regularization theorem say? It says if f maps omega into C is holomorphic, and D is a closed disk whose closure is contained in omega, i.e. D closure is contained in omega. So in other words, the boundary is a circle, the circle is also contained in omega, right? Then all derivatives of f exist. Fn of z exists for all z and d, and n and n. So every derivative exists. Beautiful, okay? And so how do we prove this? Proof. Let's draw our picture. There's our omega. There's our disk, right? And I give you a point z inside that disk. And what does Cauchy's formula tell me? It tells me that if this is my disk D, and this is the boundary, I'll call that the boundary C over there. The boundary of this is the circle C. So by the Cauchy integral formula, what would you get? You'll have that f of z is 1 over 2 pi I, the integral over C, f of zeta over zeta minus z d zeta. That's what Cauchy tells me, okay? There are no derivatives in this formula, but let me examine what happens when I consider the difference quotient, okay? So now, consider f of z plus h minus f of z over h, okay? What will that tell me? I know this limit's going to exist, right? And moreover, what is it? So this limit over here is equal to what? This is going to be equal to 1 over 2 pi I, the integral over C, okay? And if h is sufficiently small, then it's also going to be in this disk over here, right? So if h is I want h to be small, so if z is on the interior, if h is small, so is z plus h, right? So I can use the same formula, I can replace z with z plus h. So this is going to be f, they're both going to have an f of zeta. The first term is going to have a 1 over then z minus zeta minus h minus 1 over zeta minus z d zeta. I have to divide everything over here by h, right? So I have to put an h in the denominator. Okay, excellent. That's my difference quotient. And so I can just simplify this. This is 1 over 2 pi I integral over c with an h down over here, right? And then f of zeta. And then what? And then now the z minus zeta minus zeta minus z. So the zeta minus z are going to cancel out. I'm just going to have an h on top, right? So let's see. So I'll have this over here minus this over here. So I'll have a positive h on top over zeta minus z minus h. And then zeta minus z d zeta. Easy enough. Oh, look, the h is going to cancel out. Beautiful. H cancels out. And so now, of course, since z minus h and z are interior to this, I know that this expression here will converge uniformly to zeta minus z. So if I let h go to 0, I have the f prime of z, which I know exists, is therefore going to be what? It's going to be 1 over 2 pi I, the integral over c of what? Of f of zeta as h goes to 0. As h goes to 0, this is zeta minus z, so I have zeta minus z squared. Zeta minus z squared dz. Beautiful, right? So I get a Cauchy integral formula for the derivative. So this is the Cauchy integral formula for the derivative. For f prime. Excellent, okay? It's now, of course, there's two ways of doing this. I can simply plug the formula in for f prime and integrate by parts. That's one way of doing it. But let's just do one more calculation over here. So what would f double prime be, right? So if I do f double prime, I have to look at this formula, and then I have to plug in the difference quotient, right? So now consider, I want to get one more derivative out of this. Now we'll show that I can turn the crank. If I can do it for this, I can do it for all of them, right? So what would f prime of z plus h minus f prime of z, all divided by h look like for the next difference quotient? This is going to be a 1 over 2 pi I, then there's an h, I'll put there this time, the integral over c, f of zeta, and I have the difference of these two things over here, 1 over zeta minus z minus h squared, and then minus 1 over z minus zeta squared, okay? Now I can do the same trick over here. I'm just going to do the difference of two squares. This is the difference of squares over here, so I can pull out a factor of this. I can pull out this exact factor over here, right? The difference of these two things. So I can pull out this exact factor, and it will be left. So this is going to be 1 over 2 pi I h integral over c f of zeta, and then times the factor h over the same thing we want, zeta minus z minus h times zeta minus z, like that. And then what's left over, if I pull out a, then I always have an a plus b, so I'll have this plus this, right? 1 over zeta minus z minus h plus 1 over zeta minus z d zeta. That's just algebra. All I've used over here is the following fact. All I've used is the fact that I have an a squared minus b squared minus b squared is a minus b times a plus b. And a minus b happens to be what? The same thing we started with, right? So now the h is going to cancel, and as h goes to 0, what does it converge to? As h goes to 0, this is going to converge to 2 of these things, so this is going to be equal to 2. It's going to be 2 over 2 pi I as h goes to 0. The integral over c of f of z zeta over zeta minus z to what power now? So over here, all the zeta minus z is zeta minus z, and then 2 zeta minus z, so it's going to be a zeta minus, there's 2, then zeta minus z cubed d zeta. Beautiful. So this is a formula for what? For f double prime of z. Awesome. Okay? In particular, what this shows is that if f prime exists, then f double prime exists. That's remarkable. That's a remarkable fact. That's a regularization is a very, very powerful tool. All I'm telling you is I'm saying you can do one limit. Then regularization says you can do 2 limits, 3 limits, 4 limits, 5 limits, 6 limits, 7 limits, 8 limits, 9 limits, and as many limits as you wish, right? Very, very powerful mechanism. And so in general, so now you can just turn the crank. That happens to be 2 factorial if you wish, right? And so in general, if you're doing induction, so using induction, the induction proof is easy. We see that fn of z, the nth derivative of the function at the point z, is n factorial over 2 pi I, the integral over c, and then f of zeta over zeta minus z to the power n plus 1 d zeta, and that is the Cauchy integral formula for the nth derivative. So this is very, very, very exciting stuff over here, because what this tells me is that this is a first sort of tool that shows a priori that some PDEs, some partial differential equations, exhibit this beautiful phenomenon called regularization, right? The Laplace equation satisfies the same thing, so does the heat equation, and then the rubber really hits the road when you start talking about the wave equation, because the wave equation has finite speed of propagation. So there's a lot of theory that goes into the fact that saying that it's instant. So in other words, if some of these PDEs that you give you very rough data, and the PDE takes the rough data and instantaneously regularizes it. Beautiful. And the Cauchy formula is one of the first illustrations of this, right? That you can basically differentiate the kernel as much as you want, and that's exactly what I'm doing. You can sort of see over here that what have I really done over here? I've really taken my kernel of zeta minus z, and I took the first derivative. The first derivative was what? The first derivative of 1 over zeta minus z is really a 1 over zeta minus z squared. What's the next derivative going to be? It's going to be 1 over zeta minus z cubed times 2. Oh, look. What's the next derivative? 1 over zeta minus z to the fourth, and then we have a what? Then we have a 3 times 2. Oh, 3 times 2 is 3 factorial. That's exactly what I'm doing over here. So I did this in the difference quotient way, but I encourage you to do it by differentiating the Cauchy kernel and seeing that the same formula is true. Now, what we'll do in the next video is we'll take this formula over here, and we'll actually show that I can use this formula to get one better than C infinity regularity. So in other words, this says that all the derivatives exist. There's something better than all the derivatives existing. You might say, what's better than all the derivatives existing? What's better than all the derivatives existing is that a function has analytic or has a Taylor series representation around a point. So Taylor series is better than just being C infinity. And in fact, these holomorphic functions over here not only are regularizing C infinity sense, they also regularize in the analytic sense. And we'll prove that in the next video. Thank you very much.